So let's have a look at June 2018, paper 2, Aromatic Chemistry, the chemistry of benzene. So it's asking you now about benzene. Explain the bonding in benzene. So benzene is the one on the bottom left, the sort of 6-carbon ring with a circle in the middle there. So what do I know about it? Well, I know that each of those corners has got a carbon, so there's 6 carbons in a ring. I know it's flat, it's planar. Every carbon has 3 bonds, well, 3 normal covalent bonds, 1 to a carbon on either side, left and right, and 1 to a hydrogen that's on each of those corners. So where's the 4th electron? Because after all, carbon's in group 4 with 4 electrons in its outer shell. Well, that's a p electron, and that p electron goes up and down, above and below the ring in a figure of H shape. So it's delocalized, it's sometimes above the ring and sometimes below the ring, it's moving. And each of those orbitals, those figure of 8 orbitals on each of the 6 carbons overlap, and that adds extra stability. All of the bonds between the carbons are perfectly symmetrical and perfectly equal in length. Let's have a look at the enthalpy data then. When a hydrogen adds across that double bond with electrophilic addition, it releases 120 kilojoules per mole of energy. How do I know that energy is released? Because it's minus, it's exothermic. So surely when I add 3 hydrogen molecules instead of 1 across the to the ring, it should be minus 120 multiplied by 3. It should give out minus 360 kilojoules per mole of energy, but it doesn't. It only gives out minus 208. So it doesn't give out 152 kilojoules per mole of energy. It's not giving out that missing amount of energy. It's giving out less energy than it should do. It's giving out 152 kilojoules of energy less than it should do. That means it's more stable. Something that gives out less energy is more stable. Something that gives out a lot of energy, say for example a firework, is unstable. So the fact that it's not giving out that 152 kilojoules of energy means that it's much more stable than expected. Okay, question 7, 7.1. Acyl chlorides are useful reagents in synthesis to react with aromatic compounds. So how do I get an acyl chloride such as propanol chloride onto the ring? So if you've got an acyl chloride, something with a COCl, you need an aluminium trichloride catalyst, AlCl3. It removes the Cl and leaves a plus charge on the C. So it's CH3CH2CO with a plus charge on the C. You don't really need to draw the displayed form as I've shown there on the right hand side. You can just put CH3CH2CO with a plus on the C, and the Cl comes off and bonds to the AlCl, and that becomes minus charged. And then that means you can have a mechanism. So the electrophile, the COCH2CH3, the C plus OCH2CH3 is an electrophile. It's electron pair acceptor. It accepts electrons from the ring and it bonds onto one of the corners, one of the carbons of the ring. At that point in the mechanism, you need to show the H on that corner as well, because we'll lose that in a minute. You need to show a horseshoe with a plus shape of the ring. After all, electrons have been given away from the ring, so that becomes plus charge. Electrons have bonded, gone towards the C plus and bonded to that C, so that C plus has lost its charge. It's in the ring now. You need to draw a horseshoe with a gap towards where the COCH2CH3 and the H are, and the edges of that horseshoe need to go no further than the 2 corners either side of where the COCH2CH3 and the H are bonded on. Then a bond breaks and arrow goes back into the ring. It will release H plus, and the ring will be reformed again with a circle with no plus in it. Incidentally, what happens to that H plus, that will react with the AlCl4 minus, it will reform AlCl3. That's how you show that it's a catalyst, and it will make HCl or H plus Cl minus, which will form HCl, hydrogen chloride, as white steamy fumes.